Hello and welcome to this week's video. Now we'll only be talking about alibre again today. Hopefully we'll get the any parametric series back next week. But this is going to be a very interesting one. So you can see on screen that I've designed something that looks like a valve handle. Okay, so we've got a tube that's bent around, and we've got a bit of sheet metal for the hub and the spokes. And we weld it all together, and this could very well be a valve handle. Only problem is I haven't seen a valve stem that's triangular, right? Ever, actually. So we need to make this at least a square or a hexagon. I've seen square valve stems, and I've seen hexagonal ones, but no triangular. So we'll need to change that into a square, let's say. So I go into the equations I've prepared, and I change this polycount value here, and we have a square. Okay, and if I change this polycount value into a 6, we will get a hexagon. And if I changed it to a 7, we would get a heptagon, which is equally as absurd for a valve stem as the triangle. But what's going on here, right? Well, I will be showing you today how to create parametric regular polygons. And let's see, is this the little triangle that I mentioned in the title? No, this is the one, right? This is the little triangle that could make any regular polygon, and I call it the generator triangle. And the idea behind it is this. Let me just show my sketches. The idea behind it is this. You can slice any regular polygon to equal slices that have an internal angle of 360 divided by the count of the sides, right? So pretty much like you would slice a pizza in equal pieces, although we know that's impossible and somebody always gets the smaller piece. Get back to polygons. So when you do that, when you slice a regular polygon into triangles, you get isosceles triangles that have an internal angle of 360 divided by the count of the sides, as I mentioned, right? And if you then cut that or create that generator triangle and pattern it around, you will get the regular polygon. So if you see, here's the pattern. If I go back, here's the cut I made. So this is my generator triangle, right? If we go into the sketch, you will see, okay, so I switched off the dimensions somehow. Anyway, so you will see that I've made a triangle. It's an isosceles triangle because I've made these equal constraints. I've told it that it has an internal angle of 360 divided by 3 because I want a triangle. And I've also defined it as to be always within a circumscribed circle of 20 millimeters. So this is the circumscribed circle of the resulting polygon, right? So this is how you define that. And if I go into the equation editor and change this into a 4, right, which is how I made the square before, you will see that all that's going on is that this internal value switches. 360 divided by 4 gives 90, right? And then I make this cut, I pattern it around, and I get the square. And if I change that into a 6, this becomes 16. That's how I get the hexagon. And if I change this into a 7, I get this value, right? And that can't be right. I should change my units precision. Let's see if we can do that on the fly. Units. So angle precision, let's give it 3 decimal places. Okay, so you can see that we get a very weird number, right? Because it's a 7. But it's a precise number, and that's how we get the heptagon. So that's the way to get regular polygons, right? From this little sketch, which I call the generator triangle. But so there you go. Right? This is the generator triangle, and it generates a hexagon now. But there is another application for this, and I'd like to show it to you. And it'll be fun to make it from scratch, right? So if we go back and we make a new sketch, so I found another use for this method, which was in a project I'm working on with lab automation, right? We wanted the platter on which we could mount some holders, so we can spin it around and present a different holder every time. But we wanted to have platters with different counts of sides. Okay, so there we go. Prime example for this method. So let's say we want this to be 125, right? Let's go make our variables. So we'll make the variable poly count. It's going to be 3, and it needs to be a count value, so unitless. Let's make our angle value, poly angle. So we'll write here 360 divided by poly count. Okay, so it's not throwing an error at me, angle type. It's not throwing an error at me, but if I hit apply, the value is wrong. And the reason the value is wrong is because of the dimensions. So I am dividing 360, which is a unitless number, right? I haven't put any units behind it, by another unitless number, which gives me the result 120, but without units. So when alibre tries to change that result into degrees, it gets 35 for some reason. This is a useless number anyway. So the way we fix that is we need to tell it that you are dividing 360 degrees, right? Now it knows we're talking about degrees, and it just gets it right. It gets the right result as a value. And I'll show you another little neat trick. If you have Windows 10 or later, you can hold the Windows key and the dot and hit the dot, and you get this menu where you can add all sorts of weird stuff to your text. And if you go to the characters, general punctuation, and you scroll down a little bit, being careful not to miss it, you will see that we have the degrees symbol here. And I find it amazing that alibre understands that, right? If you put the degree symbol there, it knows you're talking about degrees, and it will perform the division correctly. Okay, so we made this. Let's hit OK. Okay, let's go and assign our value to this angle now. This is the poly angle. Oh, haven't I? Poly angle. Yeah, well, whatever. Be careful not to make any spelling mistakes when creating your variables. So this is fully defined now. Okay, and let's extrude that. Let's give it a thickness of 8 millimeters, I think is enough. Okay, and let's say that we want to mount stuff here, and our mount is just a couple of holes, right? So I want to put a couple of holes here, 5 millimeter holes. That's fine through all. The way I create these holes is I place them, and then I fully define where these things are. So I'm going to use my midpoint constraint tip. So I click this and then this. So I've now defined a line segment, and then I click here. So these are always so this origin is always on the perpendicular bisector of the line segment that is defined by these 2 points. I'm also going to make them horizontal. I'm going to say that these things are 60 millimeters apart, and that they are 5 millimeters from the top. Nah, 6 millimeters from the top. There we go. 6. Okay, there we go. Okay, so let's say that we need these two holes to mount our holders or whatever. Okay, so we've got everything we need now, and let's make our parametric platter. Okay, so we create a circular pattern. We want to pattern the extrusion and the holes. The instance count is the poly count variable we created, and the center is the z-axis, basically, the way we defined this, the way we designed it. Talking about design intent again. So if we hit OK, there you go. Now, look what happens when I go and change the poly count value to a 6. Right? Let's change that to a 6. Hit OK. There you go. We have a platter that can take 6 of these mounts. And because we need this side to be of a fixed length, because we're mounting something there, and that length cannot change, as we're increasing the side count, this thing becomes larger. Okay? So 8 sides, octagon, 12 sides. I suspect this would be called a dodecagon. And you see that we can spin this around and present a different mount each time, right? We can have a hub in the middle. That's very easy to design, actually, as soon as you know how to create that regular polygon. So that's it for today. How to create parametric regular polygons and 2 use cases for it. I hope you found it interesting. If you did, subscribe for more videos like that. If you liked it, hit like. If you didn't like it, do hit dislike. I still want to know if you didn't like it. And I'll see you in the next one.